Hey friends, welcome to this lecture about summary statistics, tables, and interpreting results. It sounds like a bunch of things to learn today, isn't it? If you are new to this course, my name is Enoch. I'm a research assistant at the Department of Medical Epidemiology and Biostatistics at Karolinska Institutet. A part of the teaching materials here was based on Anna Lam's teaching in Applied Epidemiology before. Some other resources and references can be found below as well. In this lecture, I want to show you how to do some basic summary statistics and analysis. I'm a Stata user, so if you are using R, SAS, I believe you can still find other excellent resources online, whereas you are still mostly welcome to participate in this class. I will also show you some bad examples, just to remind you not to make the same mistakes. Then I will give you some principles of making tables and how to make them as well. If you're a student in epidemiology, you probably have already heard or even learned about rate, proportion, risk ratio before. I will give you a short review on these basic epidemiology terms and help you recapture the concept and interpretation of them. Then the last part, we will dig into how to calculate risk ratio, odds ratio, and incidence rate ratio using Stata. Here comes summary statistics. First, it's about measures of central tendency, mean, median, and mode. Mean is the average of the values, the sum of the values of a variable, divided by numbers of the observations. Median is the 50th centile of the observations. Mode is a value that occurs most frequently. You probably know this really well already. This is just a recapture. In Stata, you can use tab_stat variable to obtain the mean of the variable. And if you specify by statistics parenthesis, you can get count, mean, median as well. The second part of summary statistics I'm going to talk about is about the measures of dispersion. Range, interquartile range, variance, standard deviation. Range is the difference between the maximum and the minimum, and interquartile range is the absolute difference between the 25th percentile of the observations and the 75th. Variance shows the spread of the data. So in Stata, still the same, using tab_stat and specify what you want to know about the dispersion of the data. It is easy for sure, whereas to know the central tendency and dispersion, pretty much they will give you a big picture of the data itself that you're looking into. So you will know the distribution of the variable. Next, let's move on a bit. I would like to show you one bad example of table. Let's take a look at this one. I would say the main issue here is that they listed all the estimated parameters, and there were just too many decimals. And let's talk about the basics of making tables. It would be nice to first elaborate the principles of making tables. Headings, same as headings in graphs, should be self-explanatory with sufficient information, and they should be placed above the tables. Remember that when we talk about graphs, I said the headings of graphs are placed below the graphs, whereas for tables, they are placed above the tables. They should be numbered sequentially. And next, please don't insert tables directly from the program's output. No screenshot, please. Why? They look ugly. That's a simple but correct answer. You should definitely rearrange your table in Excel, Word, or LaTeX, depends on you. and no vertical lines, and only a few horizontal lines, as few as possible. Normal spacing with a font of 10, but this one is optional. And this one is also from my own work of my master thesis. Let's take a look together. Heading, yes, table 1. Baseline characteristics of blah blah blah. Is it placed above the table? It is. The heading itself, it was placed above the table. Is it from the output of Stata? Nay, it is not. I rearranged it in LaTeX. I didn't have vertical lines and only a few horizontal lines. Let's move on to one-way tables. There are different ways to tabulate the data. I will just quickly go through the most popular comments. The first one is table. Quite intuitively, you just table the variables and you specify the contents that you want. You can also call tabulate variable. Then you would it would generate the frequency of that variable. For example, here we tabulate died. The output then tells it that 25 out of 34 died, which was around like 73.5%. Another useful comment to have is table 1 underscore MC. It was actually recommended by my colleague Marlena Josephine Stropman. There are more customized functions you can play with. Please first install it using SSC install and try it on your own. I think it's interesting to play with this comment, and it's quite easy to get the things, all the baseline characteristics that you need in your table 1. Now we move on to 2x2 tables. It is always easy just using tabulate still, and you have variable 1, variable 2. For example, here is I use tabulate died jog. And actually more options are available to use. For example, you can use chi-square and Fisher's exact test. Then Stata will also do a chi-square test and Fisher's exact test for you. Just recall how to interpret it. Chi-square test is testing the association between two binary variables. The interpretation here is that using placebo has association with the patient's death or not. And for sure, you can always stratify a 2x2 table using by or by sort. Till this point, we are probably not yet satisfied because we often want to use data to generate risk ratio and odds ratio as well. And actually, there is a really useful tool in Stata called Table for Epidemiologists. You can go to the bar at the top and go to Statistics, Epidemiology and Related Tables for Epidemiologists. Then you can choose what function you want to implement. However, before demonstrating how this works, I think we need a bit, refreshment on basic epidemiology terms. So basically, there are two categories here. Yeah, it's just a recapture of what you have already learned in epidemiology. Two categories: rate, proportion. I'm pretty sure that you knew them already, and if you have ever taken any epi courses, which I believe you've done it, we are using statistics software, which a lot of time you can probably generate something based on a certain syntax. However, the interpretation plays an important role as well, so that's why I'm gonna help you to recapture all the terms. Alright, rate involves person time. For example, incidence rate is the number of deceased over the total person time follow-up. Mortality rate is the number of deaths over the total person time. Hazard rate, usually described in the survival analysis, it can be referred to mortality rate if you define death as event. Next, we are gonna move on to proportion. Cumulative incidence, it is over a period of time the number of new cases over the initial disease-free persons. You see, there is no time involved in the denominator, but you have to specify over what period. The next one is fatality. Over a period of time, number of deaths of the disease divided by number of persons with the disease. Maybe I think let's take a COVID example. Over 10 months, the fatality of COVID patients in Sweden was around 3%. You might want to recall what would happen if you don't specify the time period. Then actually, over a great number of time, for example, like 100 years, the fatality of whatever exposure, it could be COVID, it could be influenza, or just a more extreme example, a mosquito bite, let's say it. The fatality would be 100%, because after 100 years, the people of whatever disease of exposure, they would all pass away. They would have already died. Next one is about prevalence. We have point prevalence or period prevalence. It depends on, it is a time point that you measure or a period of time that you measure. And that is the number of disease over the population. That would be a cross-sectional measure. And survival proportion. It's not a rate. Please don't say survival rate. Till now that you can still see that a bunch of articles, they still say survival rate, but that is not correct enough. The denominator does not involve person time insight. It is just a group of disease-free patients at risk. It is a proportion, not a rate. And now let's have a small quiz together. What is the key difference between rate and proportion? Time. Person time is involved in rate, and usually in proportion you have to specify a period of time. Next one. What is the difference between mortality and fatality? Mortality is a rate, so it's number of deaths over the total person time. Fatality is a proportion. It's out of the people with the disease, how many die over that period. The next question, it's about risk. Is risk a rate or a proportion? What do you think? Rate or proportion? Rate is a proportion of an event by definition. For example, death. The event could be death. So estimates of risk could be measures like cumulative incidence, cumulative hazard, and this is just a typical definition in survival analysis. Cumulative hazard is a complement of survival proportion, which is 1 minus survival. It is cumulative proportion of death. Then you have risk difference, the difference of the probability of an event between the exposed group and the non-exposed, and risk ratio is then the ratio in between. Something to keep in mind is that people have different definition on relative risk, or say RR. Remember, it could be risk ratio, so that would be the ratio between proportions, or rate ratio, that would be the ratio between rate. So be aware when you see RR, you have to think about that. What are you saying? Is a risk ratio, rate ratio, relative risk? Because they could all be interpreted or say it could all be abbreviated by RR. So be aware of it as you are reading or writing some results using RR, which one that you are saying. Let's take an example. If we have a totally 7 patients here, no, it's not patient, they are people. If we have totally 7 people here, the exposed and unexposed are females and males. As my definition, and the case is having Shiba or guinea pigs as pets, then we can make a 2x2 table shown here. Epidemiologists love 2x2 tables. And cool. We can calculate the risk difference. So the risk difference between female having Shiba and males having Shiba is 2/4 minus 2/3. That would be minus 0.16. So the interpretation here is females have around like 60% lower risk of having Shiba than males. Move on. The risk ratio here is 2/4 over 2/3. That'd be 0.75. Interpretation, the risk of females having Shiba is 0.75 times than males having Shiba. This is risk. Risk difference, risk ratio. Let's move on odds. Odds is a ratio between those having and not having an outcome, given the probability of having an event is P. Then odds would be, you see here, like P over 1 minus P. You see, it needs to be a binary outcome. And odds ratio measures the association between an exposure and an outcome. Usually, it's the odds of the exposed group over the non-exposed group. So saying that the odds ratio is 0.5, indicating that there is a 50% decrease in the odds of having an outcome among the exposed compared to the unexposed. Crystal clear? A quick question. Why is there no odds difference? Yeah, when we talk about risk, we had risk ratio and risk difference. And here when we talk about odds, why is there no odds difference? Answer is simple, because it is just not interpretable to present the difference of odds. Coming back to the Shiba and guinea pigs example, 2x2 table again, the odds of having Shiba among female is 2/4 divided by 2/4, so that would be 1. And for males is 2/3 over 1/3, so that would be 2. Odds ratio is 1/2. Interpretation would then be there is a 50% decrease in the odds of having Shiba among females compared to males. So the odds of having Shiba is actually higher in males. We then say that higher odds of Shiba ownership exist among males than females. Good! That's all for the odds. I think I'm now gonna tell you like some principles that you can follow as you describe a ratio in a study. It could also be an instruction as you are reading or writing some study results as well. Usually, there are 4 components that you can follow: exposed group, ratio, outcome, unexposed. Example, females, the exposed group, have a risk ratio of 0.75 having Shiba, the outcome, compared to males, the unexposed group. Another example for odds, females, exposed group, having a 50% decrease in the odds of having Shiba, outcome, compared to males, unexposed. Another small tip on like interpreting ratio is that If the ratio is less than 1, you would do 1 minus the ratio times 100%. For example, for this ratio 0.75, that would be 1 minus 0.75 times 100%. That is 25%. You then say 25% lower risk. If it's greater than 1, you do ratio minus 1 times 100%. For example, odds ratio 2.05, you do the calculation to get 105 increased odds. That is, the odds is 2 times higher, around 2 times, or saying twice the odds. I'm happy to give you more examples. This is a case control study. The exposure is diabetes, and the outcome is tuberculosis. Let's take a look at this cell of odds ratio. It tells that people with diabetes, they had a high risk. They had a higher odds of having tuberculosis in comparison with people without diabetes. Another way you can interpret it is having diabetes was associated more than a twofold increase, because the odds ratio was 2.15 in the odds of tuberculosis compared to not having diabetes, that is the unexposed group. Another example here is about physical activity and anxiety. The exposure is physical activity and the outcome is anxiety and depression. Let's focus on this cell, 0.71. Then the interpretation would be patients who had physical activity had a 29% lower odds, because 1 minus 0.71, of having anxiety compared to those who did not. Second, it's just the same interpretation. Take a look on your own later when you look into the site. Finally, we are back to Stata. Cool. We then can use the Stata epidemiologist and related function to calculate risk. Basically, you just have to call CS and case exposed. For example, CS, die, as my definition of case, drug as my definition of exposed. For example, then you can see a calculated risk for you. You can easily see the risk difference and the risk ratio here. If you want to have odds ratio, that's also quite easy to call. You just have to add OR. Then in the output, you will obtain the odds ratio as well. And for incidence rate ratio, you need to have the time at risk. That would be the study time, the follow-up time as well, to be able to calculate incidence rate. Remember, it's rate, so person time is involved. I wish you learned a lot today. Probably also refresh your understanding and some basic epidemiology terms as well. This is something you will learn again and again, and it is important, I would say. Save the slides, and if you forget, you can always come back to update yourself. Hey y'all!